Welcome to the SEI podcast series, a production of the Carnegie Mellon University Software Engineering Institute. The SEI is a federally funded research and development center sponsored by the U.S. Department of Defense. A transcript of today's podcast is posted on the SEI website at sei.cmu.edu/podcasts.
Welcome to the SEI podcast series. My name is Suzanne Miller, and I'm a principal researcher in the SEI Software Solutions Division. Today, I'm joined by Jerome Hugues, a senior architecture researcher also in the SEI Software Solutions Division. We're here to talk about his work in assuring cyber physical systems, especially autonomous ones. Welcome, Jerome.
Thank you, Susie.
So you've done previous podcasts with us, and we will link to those in our transcript. But for those who didn't catch your earlier podcast, would you start just by telling us a little bit about your background, why you came to the SEI, and what's cool about the work that you do here?
So thank you. Yeah, so it's actually my second podcast with the SEI. I joined the SEI 4 years ago to work mostly on model-based techniques. So I'm interested in the architecture of cyber physical systems as a way to ensure that they're safe, correct by construction, and that we can also derive an implementation of the systems. My background is obviously in computer science, mostly on middleware, operating system, formal methods, really with this emphasis on architecting systems and demonstrating that they can hold multiple types of properties in terms of performances, safety, security. And for this, demonstrating that they have an actual semantics, explaining what this semantics is, and deriving tools from this semantic is critical to my work. So I joined the SEI 4 years ago as a senior researcher, and I've run a couple of projects on this particular topic. And today we're discussing one of those on the assurance of cyber physical systems, autonomous one, as you mentioned, and a couple of contributions we have made on this field. So thank you for this opportunity.
No, this is excellent. And, many of us at the SEI work on cyber physical systems, which are systems that rely both on the hardware and the software elements to be able to perform their functions. So neither alone will actually perform the functions that we need. And those tend to be very safety critical, mission critical kinds of systems. So assuring that the quality attributes, security, safety, reliability, are present throughout the system is one of the biggest challenges in those systems, because we tend to build things, in components, and you're not always thinking about how your component affects everything else. And so the work that we do and that you do in the model-based arena is very critical to exposing to people and illustrating what the effects can be if we ignore those kinds of quality attributes when we're building these systems. So I am thrilled to have us doing this kind of research, and I'm absolutely thrilled to talk to you about what we've done today. So let's get into the topic. So we want to think about, we like to think about having more data is a good thing. And we outfit autonomous, which are cyber physical systems that actually work on their own in many of the settings that they're in. We give them more and more sensors and better sensors to give us higher fidelity data and give them more data to operate in their environments. But that's not enough, right? So can you talk about the challenges that come with adding more data, more sensors to these systems as we become more technologically mature and being able to outfit them?
Yeah, of course. So when you think about it, so first of all, why do we need more data actually for those systems? We need more data because we want to be more precise in evaluating the situation and making decisions. We want our systems ultimately to replace us for a couple of mundane tasks, the one we don't really want to do. Autonomous driving being one example, out of many other type of autonomous systems we can think of. So we want to have more data so that we can take more precise decisions. As we are collecting this data, we have to think in terms of what is the implication for the system we are building. Because more data means, first of all, more computations that we'll have to execute, more complex ones. So in terms of algorithmics, of course, in terms of mathematical domain, it has a lot of implication, and there is a whole area of research on how to do reinforcement learning, how to do autonomous decision, how to build a representation of the environment, for instance, for making maps, to build maps out of the environment we may sense. But this is usually the visible functional aspect of the iceberg that we are facing. And usually below this iceberg, there is all type of other situations that we have to think about. So we have more sensor, so we do more computation, so we need more powerful CPUs. And with more powerful CPUs come more tricky questions in terms of energy management, for instance, or in terms of reliability of the processor that we want to embark. Some of us may have already experienced system, for instance, our cars crashing just because some tornadoes, some thunderstroke happen nearby. Electricity, electromagnetic compatibility are impeding reliability of the system, and we have to think about this. This is not really related to the type of research we do here at the SEI, but many other FFRDCs are really concerned with electromagnetic compatibility. Closer to what we do, more sensors mean obviously that we will have to aggregate various streams of information, various streams of data. And so ultimately the software architecture, the architecture of the cyber physical systems will be more complex.
Right.
This data will have to be synchronized. We have to make sure that, yes, the information we get from the left tire of the car is compatible and is arriving at the same time as information coming from the right side of the car, for instance. So we have to ensure that the data is correct, arriving at the right time, so without timing issue, that the data is correct. It has not been tampered with external indication. For instance, many of us, again, I'm taking car as an example. We all love autonomous cars, and I'm really looking for having a fully autonomous car, level 4 type of thing. But it's not for today. But many of us have pressure sensor on tires, and we love to check that this information is correct. This information is coming from a wireless sensor. And so it could be possible, for instance, if we look at it from a cybersecurity perspective, just to tamper with this sensor, send an incorrect data to the car so that, hey, you got a flat tire, even though it's obvious that you don't have one. But the sensor has been jammed. And ultimately, the car will not start because, hey, the car cannot allow you to start. So there's all type of issue in terms of security that comes with this additional sensor. Because more sensor, more complex architecture, more difficult it is to ensure that it is secure from a cyber security perspective. And the same issue will be observed from a safety perspective.
Right.
More information, more sensors. If one of them is not providing the right information, not just at the right time, but just even the right value, the system may consider that it is in a specific state or in a specific position, if you will, but it's not accurate. And so it may go on the left, even though there is a wall on the left. And you may have a safety situation in this particular case. So more sensors is nice from the functional perspective, but it's really a nightmare or a challenge, so to speak, from the safety, security, and performance perspective, which is what we are here to solve and address. I love those architectural challenges.
And I would argue that one of the reasons that not everyone may be as enthusiastic about autonomous cars as you are is, especially if you're not really directly involved in this work, when something like that happens, when the tire sensor says you have a flat tire and you don't, it reduces the trust in those autonomous elements of the system. It's like, why is this thing telling me that my tire is flat? It's not flat.
So you're right. In this particular case, trust is critical. And it is the reason why we have to remember that in cyber physical systems, there is this last word, system. We have to consider it from a multidisciplinary perspective. It is a system. So ultimately, what we are delivering is not just a piece of hardware or a piece of software. It is a system which is made of hardware and software. Eventually, in assurance case, a convincing argument that can be understood by an external party that the way we have engineered the system, the way we have tested it, and the underlying theories that we use to get evidences is consistent. And this was part of this activity of this project that we are about to wrap up at the end of FY23 to build this cohesive story, which is not just to say, we want to work on the architectural work, do software as usual, but really consider the system dimension of it. And you're right, ultimately trust is something that we want to achieve. And trust is something that you can achieve by convincing people and by providing arguments that what you have done is correct by construction.
All right, so let's get into sort of the detail, more of the details about this work. So there is a learning component aspect that it is fundamental to an autonomous cyber-physical system, right? Part of what makes it perform better is as it gathers data not only about the environment but about its own performance, it can make corrections, it can add precision based on learning, and we build that kind of learning into these kinds of systems. But can you talk a little bit about their role of those learning components and the challenges that they actually pose to things like safety and security and your approach to verifying the learning components?
So let me start first with this idea of learning components. So there is a lot of enthusiasm around AI topics, as you may, as we all observe. It's something great. Just the idea of dropping a couple of software elements, learn this data, and make something out of it is really exciting. The truth is, they're not really learning. If you look at it from a mathematical perspective, they're just solving some optimization problem. CPUs are very good at it. The second question, or second answer I may give is that I'm not really interested in verifying learning components in this particular project. Many other groups are working on this topic, and it's part of a very large research portfolio. Some colleagues, for instance, at Collins, have made tremendous contribution in that particular domain. What we observe, though, is that in most cases, they are interested in the correctness of the learning component itself. This is fine because this gives a verified component that we may integrate and verified with some stochastic properties, so to probabilistic property. The problem we want to address, or that we are addressing in this particular program, is the question of integrating this learning-enabled component within a system. What does it mean to take a component for which we may have a characterization of its inputs and outputs, all the data stream I'm collecting and the data stream I am outputting, with some performance metrics? I know that it will take up to a couple of milliseconds for me to tell you whether or not this is actually a horse, a bicycle, or just a tree that is on the road. And how can I integrate this component, knowing that I may be wrong into classifying this object that is on the road? And by knowing this, what we want to achieve is to integrate this component and mitigate any bad decision, any bad outcome coming from this element, so as to minimize the risk of a bad event happening in your system. And so this is really the system perspective that I was discussing just before, which is basically how can we define the architecture of the system so that for any given learning-enabled component that is part of the system, we can add proper fences around it so that whatever this component is receiving, we can assess that the value is correct, has not been tampered with, is arriving at the right time, and whatever the system is outputting can be controlled for some notion of correctness. Is the acceleration of my car within the speed limit of the state of Pennsylvania, for instance, or within the body limit, if you want to have a cool way of driving? All of that is part of this fencing that we want to put around the systems so that ultimately we can be confident, we can trust that the system itself is correct or not that wrong, compared to verifying the learning component, because this part we know is, as of today, not possible.
Well, and one of the challenges you didn't mention is doing all of the things you're talking about at real-time speed.
Oh, yeah.
For those that are not really familiar with real-time systems, one of our continuing challenges is integrating more data, integrating more function, and not reducing the speed of performance. Because if we're talking about a car, an airplane, a ship, there are time constraints that if you miss them can be, people can die. And so, we miss the mark of whatever we're trying to do. So that's, I think, the other thing about learning systems is learning systems that, certainly that I'm aware of in the lab, really tend to just say more data, more data. We were talking about that earlier, right? Just more data, more data, more data to make the learning more precise, but that actually slows down the learning.
Oh, yeah.
So the real question is how much data from where gives us the best balance of timing and accuracy and precision, and then safety. How do we defense? How do we prevent anyone interfering with the precision accuracy of that data, so that we don't end up having malicious or just incidental failures because something interfered with the data coming into the system and the decision making that goes along with the system. So you're taking on some pretty big challenges there, Jerome.
It is, yeah. And in this particular domain, because we're dealing with autonomous systems, actually NASA made a tech report on increasingly autonomous systems, because there is a graduation between basic autonomous systems, which are nothing but controllers, to fully autonomous systems. And related to this question of timing and decision making, before joining the SEI, I was actually teaching in France, in Toulouse, so a big place for aerospace industry. And every year I was reusing this same video of Ariane 5 first flight. For those of you who may not know about this one, it was a complete mess. At T0 plus 35 seconds, the rocket collapsed because of some software/system/testing errors, so probably a topic of its own, but it has been addressed in many reports. But it is definitely relevant to this discussion of autonomous system, because at the time, the operator in the room was saying that the trajectory was perfect and all parameters were nominal. The rocket, took the decision to self-destruct, because by the time the human reacted to the information he was receiving that everything was on track, this onboard CPU detected an anomalous situation and decided that the only correct course of action at this stage was self-destruction. And so the timing is going in both directions. Timing to react to external events, timing to engage with humans to make sure that we can protect them. And this is creating all type of interesting challenges to address in terms of timing. Again, these triptychs, timing, safety, security, we give the feeling that we're obsessed by those three aspects, but they are here to ensure ultimately the trust of the public that may use those systems.
Absolutely. So in doing this work, you've been collaborating with researchers at Georgia Tech on some of the approaches to these challenges. Why don't we talk about how this collaboration came about, and sort of what are the different areas of expertise that the team brings to the table, and your overall vision for taking on the kinds of challenges we've been talking about?
Sure. So on our end, my team at the SEI developed a couple of contributions on the architecture of cyber-physical systems. We started by taking the ADL, the architecture description language that we covered in many podcasts with you in the past, Susie. And what we did is to extend the semantics of ADL so that we can make a formal semantics out of it. So basically, semantics in such a way so that we can simulate ADL model in a very precise way, but also we can verify some properties on ADL models. When we have done this part, basically we can speak about or reason about the architecture of cyber-physical systems. What we decided to do, as I mentioned, was to establish a fence around those learning-enabled components, but still we need to perform fault detection, just to make sure that either the inputs are incorrect or tampered with, or the outputs are invalid. And so this is what Georgia Tech brought to this project. They are very well-known, I would say, deterministic or statistics-based techniques for detecting faults. The easiest one we may think about is some form of voting mechanism. You triplicate the system and you do a majority vote on the decision on whether you will go left or right for your system. As we are increasing the level of or the number of sensors or the precision of those sensors, we may want something that is less binary. We may want something that is looking at more precise evolutions on the signals that we receive, for instance. And so this is what Georgia Tech is bringing to this project. They have developed a couple of strategies to detect faults or attacks, cyber attacks, if you will, so that you can build fault detection mechanisms that are based themselves on reinforcement learning, so that they can look at specific patterns that are representative of either a cyber attack or a fault happening in system. And this is where the boundary between security and safety is becoming fuzzy. Because from the perspective of system, if I have a faulty sensor that is sending me periodically a value of 0, for instance, from the perspective of system, it's difficult to tell whether the sensor is faulty or whether it is an attack and someone else is tampering with my sensor. So that's why we're blurring those two aspects. But still, the idea of using reinforcement learning for looking for more aggressive fault or attack pattern is definitely relevant. Of course, there is a question of recursivity here because we want to define learning component with another learning component that may itself be wrong. But again, using architectural patterns, we can address those questions by expanding the fence around those components. But yeah, so that was basically the contribution of Professor Kyriakos Vavroudakis to this project to help us implementing and testing those fault detection, isolation, and recovery mechanism on some mission that we have implemented on UAV platforms.
So one of the things that you began at the beginning to talk about and reinforced here is that role of architecture as being one of the determinants of how you can, and what you're speaking about now, one of the things I know is that if your architecture is not modular, does not meet certain properties, then being able to isolate fault tolerance kinds of things, you have to have a very big fence if you don't have a very good architecture, which means you're actually going to be doing a lot more processing to gain that trust and verification. Whereas if you have an architecture that you can verify is amenable to these fault tolerance techniques, then you can actually not degrade the performance by actually adding in the fault tolerance. So that's a fantastic trade-off if you can get that.
It is a fantastic, it is a fantastic trade-off. So one of the work that we are wrapping up for this project is on basically a collection of design patterns that are known in the safety community for detecting, mitigating faults to switch, for instance, using a simplex architecture to switch from one version of a component to another. And you're right, there is definitely a trade-off here in, first of all, establishing the smallest perimeter, because as you said, if the fence is too big, we are not doing a good job in terms of resources that we're using. But also in defining what is a good trade-off for each of those patterns. For instance, patterns will differ in the number of redundant components they need. And as we know, more redundancy is more costly because we need more CPU, more wires, more energy. Some other patterns will take more time to make a decision or to switch from the nominal mode to the degraded mode, for instance. And so we are doing an evaluation of all those patterns, taking into consideration the cost to implement them in terms of resources, hardware resources mostly, and the timing aspect, the time to go from detecting an event to reconfiguring the system. And this is this type of practical contributions that we are delivering as part of this project. Not just the formal semantics of ADR, which is nice for computer scientists, but also this trade-off analysis that is made possible by providing careful evaluation of each and every pattern that have been documented in the literature.
So what is your ultimate vision for this search? Where are you really trying to get to over time with, because this is not a single 2-year research project to get all the answers.
No, yeah, I mean it's just one milestone out of a very I would say large research roadmap that I have that I want to develop, and I'm thankful for the SEI to allow me to execute it. So at the completion of this project, basically what we have developed is this idea of, first of all, this trade-off analysis on design pattern for safety, which is one aspect. Another aspect that we have developed is this formal semantics of AEDR that has been expressed using the Coq serial improver, which means that it is not just a document, but it is also something that we can experiment using a serial improver, so that we can develop all type of analysis. So we already did connections with scheduling analysis tools or fault tree analysis. And so the idea behind all of that is to address this question of what can we do with models when we do models-based software or system engineering. We have all type of techniques, and how far can we go into building a toolbox so that designing a system can be supported by evidences step by step.
Right.
You want to build the architecture of your system, which is nice. You will start building a couple of boxes, wires, connecting all of them. But can you make sense of this diagram? Yes, because we have this formal semantics. You have this formal semantics, you have this model, great. What can you say about the safety or the timing of system? Well, because I have this formal semantics, here is the proof that the time to detect my error is X. And all of that contribute to building this trust that we were discussing at the very beginning. Ultimately, it is this idea of rigorous model-based system engineering, going from requirements to a model and evidences, so that we can build this trust package that can be given to an external auditor so that we can say, yeah, it works. You may need multiple PhD in computer science to understand all of this, but ultimately we have a chain of trust across all those engineering artifacts that we have built. And so that's really this long-term vision that we are contributing to. The SEI, by trade, by history, developed a lot of contributions in that domain. And it is really this idea of pushing this forward, this idea of giving the right tool for making decisions on asserting systems. And this is one of those contributions that are making to this line of research.
And one of the things, I'm involved in some programs that have a very long lifespan. And so once the initial delivery is made of the cyber physical system, that's not the end of it, right? We've got 20.
It's never the end, yeah.
Right. And so one of the things that model-based systems engineering brings to that environment is the ability to analyze and play with the model before you actually make decisions about what the next evolution in the system or the next modernization is. And as technology evolves, can we bring this technology in? We can model things before we make those decisions, which is much cheaper than a flight test, for example. And so I'm just coming back to this again, the trust level in those models, their ability to evolve, their ability to reflect different aspects and to be able to mitigate security issues, safety issues in a trusted way, the importance of that just keeps going up. And so, having these more formal ways of assuring people that yes, we really do understand the behavior, and yes, we can predict the behavior, and yes, we can safely change the behavior. Those are just critical. So don't go anywhere. We need you for quite a while here.
I won't go anywhere. I'm happily working at the SEI. So yeah.
Good. All right. So that we like to emphasize transition. Now we're very early in this research. I mean, I'm guessing that a lot of the things you're talking about, if I were to look at them, I'd roll my eyes up in my head because they're not in my area of expertise. But if someone has become interested through this podcast or other means in learning more about assuring autonomous components in cyber physical systems, where do you go to learn more about this besides going and looking up Jerome and having a coffee? What are the resources that are available for learning more about this area?
So first off, it's part of a project, and I just realized that we did not name this project. So it's called SAFIR, for safety analysis for time-intensive cyber physical systems.
Every project has to have an acronym.
Oh yeah, and SAFIR is a small version of it. And actually, we made already 2 research review videos on this project. So definitely, there are starting resources that are relevant to give you some insights of what we have done in the past. And there is a couple of technical reports that we're finishing as well. And as usual, any of the paper we have written during the project is also available on the SEI digital library. So all of this will be linked, I suppose, when this video will be edited. So all of that will be available there. But as we did this project, we made something like 15 different scientific papers at different level of depths, technical depths and scientific depths.
Great.
So all of that is a good starting point. And as always, as we're working for the SEI, we're always excited to receive emails from interested parties to push the discussion further.
Yes. Excellent. So beyond moving forward with SAFIR, what else are you working on? that we can talk about in the future? I know the answer, but I'm going to let you tell me.
Yeah. Actually, it's kind of a continuation. I mean, each project I build is one stone in this big garden. So in this project, we were interested in capturing the model itself, its semantics, connecting it to other aspects. In the follow-up project, what we'll look at is the modeling process itself. What can we tell about the modeling process so that instead of saying, oh, let's do SysML model, let's do AEDR model, we can tell you, okay, this is your problem, and this is the way you may address it by applying modeling techniques this way. And the idea of this project ultimately is to give a map, so to speak, of modeling processes and modeling activities, because by training, by experience, I know how to model a system so that I can perform safety analysis. But this is something that is very difficult to convey in a particular way. So we'll be looking at techniques, first of all, to document those approaches and to train people to do this. But as we are defining those modeling processes, the other question that is relevant for our DoD colleagues is how much does it cost in time and money? And how can I be sure that whatever I receive from my contractors is what I expected? And so there will be this question of defining some quality attributes for modeling processes. So I'm really looking forward to this new project, a little bit less formal, but definitely addressing what I believe is interesting, which is how to make model-based techniques much more efficient and easier to transition in the industry.
Excellent. Yes, and I'm looking forward to that research as well, since that's a particular area of interest for me. So, Jerome, I thank you so much for talking with us today. It's taken us a little while to sort of be able to get together to do this, but so worth the wait. And I want to remind our viewers that we will have links to SAFIR and all the resources the resources you mentioned from the project in France in the transcript, so people will be able to access those. And a reminder to our audience that our podcasts are available everywhere you can think of: SoundCloud, Spotify, Stitcher, Apple, Google, and of course, my favorite, the SEI's YouTube channel. So I hope that you will enjoy viewing this video and learn some things and be able to sort of expand your views of what's important about assuring these autonomous cyber physical systems as we move more and more into the autonomous world. Thank you once again, Jerome. I look forward to our next chance to have a conversation.
Thank you, Susie, for your time and enthusiasm in helping us, advocating for what we are doing. Thank you so much.
Absolutely.
Thanks for joining us. This episode is available where you download podcasts, including SoundCloud, TuneIn Radio, Google Podcasts, and Apple Podcasts. It is also available on the SEI website at sei.cmu.edu/podcasts and the SEI's YouTube channel. This copyrighted work is made available through the Software Engineering Institute, a federally funded research and development center sponsored by the U.S. Department of Defense. For more information about the SEI and this work, please visit www.sei.cmu.edu. As always, if you have any questions, please don't hesitate to email us at info@sei.cmu.edu. Thank you.